Hi everybody, welcome to this video about integration formulas. This is the second video in this section on integration. So in this video we're going to learn some formulas that allow us to calculate a range of different indefinite integrals. Many indefinite integrals can be calculated by reversing derivative formulas. It's helpful to remember that integration is the inverse of differentiation. If you'd like to revise some material on differentiation, I have some other videos on my channel which go into more detail on that topic. So a very useful reminder is that when you're calculating an integral with respect to x, the answer that you're looking for is something that, if you differentiated it with respect to x, that'll give you the function that you are integrating. And this is because integration is the inverse of differentiation. So this allows us to check very easily if our integration solution is correct. We simply differentiate the solution. And if you get the function that you started with, it's correct. To start looking at integration formulas, we're going to start with the formula for x raised to the power of n. And here we've got that displayed at the top of the screen. So we can read this formula as the integral of x raised to the power of n with respect to x is equal to x raised to the power of n plus 1 all over n plus 1 plus c, where c is our constant of integration. And there are some conditions for using this formula. One is that n is not equal to minus 1. That's actually a special case that we'll see later on. And also n should be rational, so it should be able to be represented as a fraction using integers. So looking at this formula and to try and understand it, it is helpful to remember that integration is the inverse of differentiation, and we can see why the above formula is valid by finding the derivative of the result, the terms on the right hand side of the equal sign. The derivative of the result is x to the n, bringing us back to the function that we started with. If we remember, the power rule for derivatives is df dx, the derivative, is equal to d over dx, the derivative with respect to x, of x raised to the power of n. According to the power rule, that's equal to n multiplied by x, where x is raised to n minus 1. So finding the derivative of the result of the top formula gives us x raised to the power of n. Again, our derivative with respect to x of x raised to the power n plus 1 all over n plus 1. To evaluate that using the power rule, we multiply by the power, so we multiply by n plus 1, and we end up with the n plus 1 cancelling out above and below, which leaves us with x raised to the power of n plus 1. We subtract 1 from the power and we get x raised to the power of n. So we can see that by differentiating the result on the right hand side, that brings us back to the function that we started with. So remember, when you're calculating an integral, the answer that you're looking for is something that, if you differentiated it with respect to x, that'll give you the function that you are integrating. So this is our first formula that we're looking at, and that this is a formula that we can use to evaluate integration. Here we're going to look at another formula as an example. So we're going to look at the integral of dx, or as we'll see later, dy, or dz. So this formula is shown at the top of the screen, and we read it as the integral of dx is equal to the integral of 1 dx, which is equal to x plus c, where c is our constant of integration. So the key here is to remember that the integral of dx is equivalent to the integral of 1 with respect to x. And if we differentiate the result x with respect to x, we get the formula that we started with, 1. If we remember from the power rule, the derivative with respect to x of x raised to the power of 1, well, by the power rule, that's going to be equal to nx, where x is raised to the power n minus 1. So in this case, a value of n is equal to 1. So our derivative is going to be equal to 1 multiplied by x, where x is raised to the power of 1 minus 1, which is equal to 0. So x raised to the power of 0, that's going to be equal to 1. So we get 1 times 1, which is equal to 1. This shows us that our result is valid. The derivative of the result is equal to the function that we started with. It's helpful to remember that this formula is valid regardless of the letter that we choose to represent the variable. So the integral of dy, that's equal to the integral of 1 dy, which is equal to y plus c. And the integral of dz, that's equal to the integral of 1 dz, which is equal to z plus c, and so on. So this is another integration formula that we're going to look at. This is for sine kx, where k is some constant. So our formula is displayed at the top of the screen, and we read it as the integral of sine kx with respect to x is equal to minus cos kx over k plus c. So what we're doing here is we're applying the chain rule formula from differentiation in reverse. Our result is a composite function where y is equal to minus cos u over k and u is equal to kx. If we differentiate our result using the chain rule, we should find the function we began with, sine kx. So here we've got our integration formula at the top left of the screen, and on the right we have the components of our composite function. We have u is equal to kx and y is equal to minus cos u over k. If we remember from differentiation and the chain rule, the derivative with respect to x, dy dx, that's going to be equal to dy du, the derivative of y with respect to u, multiplied by du dx, which is the derivative of u with respect to x. So we can work out what dy dx is if we work out what dy du is, and we work out what du dx is, and then multiply them together. So we can do that below here in the bottom half of the screen. We start with dy du. dy du is going to be equal to minus 1 over k multiplied by the derivative with respect to u of cos u, which evaluates to minus 1 over k multiplied by minus sine u, which works out to be sine u over k. So if we swap out what u is into that formula, we get that dy du is equal to sine u over k, which is equal to sine kx over k. So now we just have to work out what the u dx is. So we start with u is equal to kx and we differentiate it with respect to x. So du dx, that's equal to the derivative with respect to x of kx, which is equal to k. So now we have dy du and we have du dx. We just have to multiply them together. So dy dx is equal to dy du multiplied by du dx, which is equal to sine kx over k multiplied by k. The k terms cancel, giving us sine kx. So it's worked out. We've differentiated, well, to look at that formula up at the top left of the screen there, we've differentiated the result, those terms on the right hand side, and it's brought us back to the function on the left hand side, sine kx. So by similar logic, we have a formula for integrating cos kx. So if you apply the same logic as we did in the previous example, we get that the integral of cos kx with respect to x, that's equal to sine kx over k plus c, the constant of integration. So this is just a little bit about using integration formulas. Typically, you'll have a reference book or a table that's on hand that you can use to look up integration formulas, which makes this process a lot easier. We've introduced some of the formulas here, but there are plenty others, and what we're going to do is we'll cover more of them as we progress. So now in our next video, we're going to learn about arithmetic rules for integration, and that'll allow us to find antiderivatives for a variety of functions. I hope you found this video useful. Thank you for your time, and see you next video.